This is part 2 of my video series where I'm experimenting to see if I could teach basic calculus to somebody with only basic high school algebra skills. Calculus is mostly derivatives and integrals, so see my part 1 video where I explain derivatives at a really basic level, and then you'll better understand what's going on here with integrals. So here's how we do integrals in calculus. X squared equals y, but in calculus we tend to not use y. We tend to use f of x, meaning it's a function of x. So if this equation had x, y, and z, this means that we're only taking the integral of the x value and we ignore the y and the z. To get the integral, that means we want the area under the curve. X squared is a parabola, so we want to know how much area we have between, for example, 2 and 4, or x equals 2 and x equals 4. If this was a square or a triangle or a rectangle, we could use basic geometry to get that area. To get the area of a square or rectangle, you just multiply one side by the other, and the area of a triangle is 1/2 times base times height. But here we're dealing with a curve, so there are no rectangles or squares or triangles. What you have to do theoretically is divide this up into thousands of little rectangles and triangles, and then you integrate, and that's why we call this the integral, to get the area under that curve. We integrate all those little rectangles together. Here's the formula for that. I've done some other videos on derivatives and integrals if you want more details, but this will just be the basic formula that pretty much anybody could understand. We take the integral between 4 and 2 right here of x squared. We write dx here to show that we're just taking the integral of the x. So if there's a y and a z, we don't do an integral of those. To take the integral, that means you raise your exponent to 1. So x squared becomes x to the third, and then you bring that third down to a denominator right here, and it becomes 1/3 x to the third. It's that simple. You draw a straight line, and you write between 4 and 2. What this means is you just replace your x with 4, so 1/3 4 to the third, minus 1/3 2 to the third, right there. Solve it, and you'll get your area under the curve right there. This is 64/3 minus 8/3 gives you 56/3. For a mixed fraction, you can do 18 and 2/3. Now you know the area under that curve. And that's how simple this can be if you don't dive into deriving all the formulas and the complexities. Let's say you don't believe this whole integral scenario and you want some proof of an equation that you'll understand. Let's take x equals y. So that means if you go over 4, you also go up 4. Here's your line for x equals y. Notice it'll form a box or a square. Let's take the integral of this. So we want the area under the curve, but in this case, it's an area under a straight line. So we want this whole area here, which is a triangle. So let's take the integral of x equals y between 4 and 0. 4 and 0. X means the same thing as x to the first, so you raise that exponent by 1, so it becomes x to the second, and you also bring that down to a denominator in front, 1/2 x squared, evaluated between 4 and 0 to get that area under the curve, or the area under the line. Plug in 4 here, so 1/2 4 squared minus 1/2 0 squared. 1/2 4 squared minus 1/2 0 squared. That's how you use that. You end up with 1/2 4 squared. 4 squared 16, divided by 2 is 8. Notice you'll get the same results if you take the formula for a triangle, which is 1/2 base times height. 1/2 4 times 4 is 1/2 of 16, which is 8. So I thought that was kind of fun, showing that This integral works not only for curves, but for straight lines. So now when you're talking to somebody at a bar and they ask you if you have calculus or know about it, you can say, of course, doesn't everybody? I think I had that like in 3rd grade where I learned how to do derivatives and integrals. So that's it for how to do integrals. See my other video on derivatives for even more details. Now I'm going to get a little more detailed on this, so stay tuned if you're interested. Let's take our good old f of x equals x squared again and see what else we can learn from this. If we take the integral of x squared, we get 1/3 x to the 3rd, which I just showed here. This will be an indefinite integral because there's no numbers here. We can put those numbers in later. This is a definite integral because we have the numbers right there that forms the boundaries for our equation. But here, when we do an indefinite integral, that just means we can put in the numbers later, and we just want to do an integral for now. You'll get 1/3 x to the 3rd, but then we add c, and I'll explain why. That c represents a constant, so that constant could just be 0, so there's nothing here, and this is all you have. Or it could be 5 or 37 or 123. So let's reverse this and see what the original function is that we started with. This is our integral. Let's take the derivative to reverse it. Here's my integral. I scratched that out because I didn't have a plus c, so let's just take this integral over here, take the derivative of it. So you write d dx, this whole thing is bracketed, equals y prime. See my video on derivatives for that notation to explain it. It's really easy. 5 is the same thing as 5 times x to the 0. Anything to the 0 power is 1, so 5 times 1. To take the derivative, you bring your exponent down and you subtract 1 from the exponent. So this becomes 3/3 x to the 2nd, which is the same thing as just x to the 2nd. Bring your 0 down, and anything times 0 is 0. So we end up with just x squared, which is our original function. So we add the c here because if we want to reverse this to get back to the original function, that means we take the derivative of this whole thing. This whole thing is the integral. So that c could equal any number of 5, 10, or 37. When we take the derivative of it, it'll disappear, and we just end up with our original x squared right there. Integrals and derivatives reverse each other. So here we start with our original function x squared. We take the integral, and we get this right here. So if we take the derivative of this integral, we end up with the original function of x squared. What we did, this shows we took the derivative, d dx, of the integral to get the function with which we started. So if we want to take the integral of this derivative, we just take this over to here, take the integral of our derivative, and we're right back where we started, right here. So this is why an integral is also called an antiderivative, because they reverse each other. A notation for this is you can take the integral of a derivative, which is f prime of x, and that'll equal your f of x, which is your original function up here. So this is a basic calc. This video is on basic integrals. My other one was on basic derivatives. Calculus is a pretty rigorous 3-class sequence of Calc 1, 2, and 3, but most of it is based on derivatives and integrals, so this is the start of it. So now for anybody that sees this video, they can say they know what calculus is and how you use it and what information it can give you.